Hello, welcome again. We are solving some questions of production engineering. The topic is metal forming. Question number 57 from GATE 2018 ME-02 is the true stress in MPa versus true strain relationship for a metal is given by sigma is equal to 1020 epsilon 0.4. The cross section area at the start of a test when the stress and strain values are equal to 0 is 100 mm square. The cross sectional area at the time of making in mm square is dash correct to two decimal places. So let sigma is equal to k e raised power n. So sigma is your two stress and epsilon is your two strain. So and this relationship is given, that is sigma is equal to 1020 epsilon raised power 0.4. So it means k is your 1020 and n is your 0.4. Okay. So now we will convert this two stress two strain relationship into engineering stress two strain relationship. Okay, so that we can find out the area. So suppose sigma is your engineering stress and epsilon is your engineering strain, and sigma uh, relationship between two stress and between two stress and engineering stress is given by sigma is equal to sigma e 1 bracket 1 plus epsilon. Okay, and epsilon is or we can say that two strain is given as ln 1 plus epsilon. Okay, or from this we have taking antilope both sides, so it will be epsilon will be equal to 1 plus epsilon e. So we put this value here, then sigma will be your sigma will be your sigma e exponent epsilon. Okay, so now we can put the value of sigma in this relationship so that we can drive the relationship between engineering stress and true strain. Okay, so sigma e comes out as k epsilon raised power n divided by exponent epsilon. So there is a relationship between engineering stress and true strain. Okay, if we take anti-log both sides, then sorry, if we take log ln both sides, then it will be ln sigma e, and this will be your ln k, this will be your n ln epsilon, and this will be your minus epsilon l ln exponent, and ln exponent is your 1, ln e is your 1. Okay, so it will be your ln sigma e is equal to ln k plus n ln epsilon minus epsilon. Okay, so now we can differentiate with respect to epsilon. So differentiating with respect to epsilon, it will be 1 by epsilon a over 1 by sigma e d sigma e by d epsilon. Okay, and as it is constant, so differentiation is 0, and differentiation will be uh, n by epsilon, and epsilon differentiation with respect to epsilon is 1, so that is n by epsilon, and its differentiation is minus 1. Okay, so now here sigma is your engineering stress, epsilon is your true strain. Okay, so if we analyze the graph between stress and strain, so this is your true stress. Okay, this graph is for true stress, and this is your true strain, and the engineering graph, the engineering stress strain graph differs like this. Okay, so this is the point of necking, or maximum load point. Okay, so at this point the load is maximum, or as engineering stress is stress divided by load divided by original area. Okay, so it doesn't depend upon the instantaneous area. So whenever p is maximum, or whenever sigma is maximum. Okay, so whenever p is maximum, sigma is maximum. Okay, so at this point the value of sigma is maximum. So considering at the necking point, as the value of sigma is maximum, so d epsilon e by d sigma e by d epsilon will be equal to 0. Okay, because this is the maximum point. Okay, so now in this equation we can put d sigma e by d epsilon is equal to 0. Okay, so this is your 0, so it will come out as 0 is equal to 1 n by epsilon minus 1, so epsilon is equal to n. Okay, so now true strain is equal to n. Okay, so but the true strain at necking is given by epsilon is equal to ln. So this is your true strain, not the engineering strain. Okay, so two strain is given by ln LF by Li, okay, and its value is your n is your zero point 0.4, okay. So from this we can find out LF by Li, so that is 1.49182. So where LF is the length, final length at the point of necking, because we have taken d sigma e by df minus 0, so that's why we will take the final length or length at the time of necking, okay, where this condition exists. Okay, so LF by Li is your 1.49182. Okay, so now in plastic deformation we know that the volume remains constant, so final volume will be equal to initial volume, so AF into LF will be equal to AI Li, or we can say AF will be equal to AI Li by LF. So AI is your 100, that is given, initial area is given, that is 100 mm square, and Li by LF we have just calculated. So LF by Li is just 1.49182, so final area is your 67.03 mm square.